I would like to thank the organizers for having me here. Okay, so I'm going to talk about joint work with Koemo Irie, and golodness and tightness are properties of simplicial complexes, which have been studied in very different contexts. And recent results on polyhedral product by recent results, it seems that these properties may be related. So I'm going to talk about these a relation between these two. Right. So this is the plan of my talk. I'm going to first talk about or define Golod complex and then a tight complex. And at last, I'm going to present my main results and its corollaries. Okay? So first, Golod complex. Okay, let F be a field and let S be a polynomial ring over F, finitely generated polynomial rings. And we set the degree of generators to be 2. Okay? And let R be the quotient of S by the homogeneous ideal. So it's a graded Noetherian ring. Okay, so there is coefficient-wise inequalities involving the Poincare series of torsion algebras of R and S like this. Okay. Oh. And the golodness of what is defined for the Noetherian ring R by the equality in this inequality. So here's the definition. We say that R is Golod if the equality holds. And there is a nice topological equivalent statement for golodness like this. Let K of R to be the Kozu complex of R. And so its homology, Kozu homology, is isomorphic to the torsion algebra like this, and which appears in this inequality here. All right. The Golod proved that the ring R is Golod if and only if all products and massive products and higher massive products in Kozu homology of R are trivial. So, so you can see that this is really hard to check because we have to check all triviality of all products and all massive products and all higher massive products. It's almost impossible. But this is really interesting property of a Noetherian ring. All right, let's define Golod complex. Let K be a simplicial complex with vertex set bracket M. Bracket M is the set of integers from 1 to M. And then we have a Stanley-Reisner ring over the field F like this. Okay, then we the general problem about simplicial complex I'm interested in is this. Given a property of a Noetherian ring, like golodness or Koema-golodness and some other things, then find a characterization of it for the Stanley-Reisner ring of K in terms of the simplicial complex. Okay, so this is an interesting problem, but it's really hard in general. And this time, we choose golodness for the property of Noetherian ring. So here's the definition. A simplicial complex K is F Golod if the Stanley-Reisner ring of it over F is Golod. Okay, let me sit down. I have a bad foot. Okay, so here are examples of Golod complexes and non-Golod complexes. Okay, so the Alexander dual of Cohen-Macaulay complex, which appeared in the talk of Stephen, is Golod over any field. Is Golod. And the second example is non-Golod complex. The square graph C4 is not F-Golod because its Kishimoto homology has non-trivial products. And the final example says that the Golodness depends on the ground field F. I mean, there is a triangulation of RP2, which is Golod over the rationals, but not Golod over the field of two elements. Right. And here's our problem in this talk. Find a combinatorial characterization of F-Golod complexes. Okay. All right, here's the definition of, there is an approach to this problem by using moment angle complex. And here's the definition. And I skip it because all of you know this definition. Okay, and the important point is this. The cellular chain complex of Zk is homotopy equivalent to the causal complex of f of k. So then we can say that if the moment angle complex for k is a suspension, then k is F-Golod for any field f. So that's why we are interested in desuspending BBCG decomposition, which was given in a lecture of Stephen last week. All right. And my approach to the desuspension of Zk is the fat wedge filtration, which I developed with the theory with Cohen-Moynier. And here's the definition. Okay, let Zki be the subset of Zk, which consists of points x1 to xm, such that at least m minus I of xj are the base points. I mean, this is just the intersection of Zk and the generalized fat wedge. So there is a filtration like this, okay? Which start with the point and end up with Zk. And we call it the fat wedge filtration of Zk. Of course, we can define this filtration for any polyhedral product, but for simplicity, let's consider the moment angle complex only here. Okay, here's a theorem. The very important theorem to desuspend the moment angle complex for K. The fat wedge filtration is actually a cone decomposition. I mean, Zki is obtained from Zki minus 1 by attaching some cones. And moreover, the attaching maps of cones are explicitly described in terms of K. I mean, there is a very explicit combinatorial description of the attaching maps of K, of cones, right? So if these attaching maps are trivial, all of these attaching maps are trivial, then Zk is a suspension, right? So that's the next theorem. The moment angle complex Zk is a suspension if and only if the fat wedge filtration is trivial. This means that all attaching maps are trivial. So we can say that the fat wedge filtration is trivial, then Zk is a suspension. And we can also say that the converse is true. This is because Zk is simply connected. Actually, we can consider the same argument for the real moment angle complex, but in that case, the triviality of fat wedge filtration implies that the real moment angle complex is a suspension, but I don't know the converse is true or not. That's really a difficult problem related to some algebraic K theory, actually. Okay, so here's an example of desuspending results using fat wedge filtrations, which already appeared in the talk of Steven this morning. Like a sequentially Cohen-Macaulay complex, which is a generalization of Cohen-Macaulay complex. It's a non-pure version of the Cohen-Macaulay complex. And totally homology fillable complex, which is a generalization of the Alexander dual of sequentially Cohen-Macaulay complex. And we can prove that if K is a totally homology fillable complex, for example, the dual sequentially Cohen-Macaulay complex, then the fat wedge filtration of ZK is trivial, so ZK is a suspension. All right. So this recovers the classical result saying that the dual sequentially Cohen-Macaulay complex is Golod. Right, here's another result. We say that K is K neighborly if any sigma in bracket M with cardinality K plus 1 is a K simplex of K. So K includes the K skeleton of delta to the M minus 1. And the result says that if K is half of dimension K neighborly, then the fat wedge filtration of ZK is trivial. That is, ZK is a suspension. Right. And by using the fat wedge filtration technology, we can prove more results on the combinatorics of simple ratio complexes. Here's the one-dimensional result. Okay, if K is a graph, then the following are equivalent. K is Golod. K is Golod. Golod means that any minimal cycle in K is a triangle. And ZK is a suspension. These are equivalent. And of course, from this result, we can easily see this corollary. Triangulation of a circle is minimal if and only if it is a triangle, of course, because the only chordal triangulation of a circle is a triangle. So, and of course, a triangle is the minimal triangulation of a circle. Right, here's a two-dimensional result. If K is a triangulation of a closed F-oriented surface, actually we have a result on a general two-dimensional complex, but here I state the result for the triangulation of a surface only. If K is a triangulation of a closed F-oriented surface, then the following three conditions are equivalent. K is Golod, K is one neighborly, ZK is a suspension. All right, now here are important remarks. The first one says that most of one neighborly triangulation of surfaces are minimal, minimal triangulation. So in most cases, triangulations of surfaces Golod if and only if it is minimal. Okay, this is true for one-dimensional case like this, and in most cases, it's true for, it's also true for two-dimensional, in two-dimensional, okay? Right. That the second says that the second remark is about the general two-dimensional Golod complex, and it's characterized by one neighborliness and some other conditions of homology. Okay, I'll skip here. Okay, so in 1 and 2 dimensions, Golodness is related to Golodness of a triangulation of a manifold is very close to the minimality of a triangulation. A minimal means that the number of simplices in every dimension is minimal. Okay. Right. So then we can pose this question. We can ask this question: is Golodness of manifold triangulations related to minimal triangulations? All right, Golodness is defined purely algebraically, but this is a new insight to the Golodness, okay, which was obtained by the results on polyhedral product. Right, so the second part is about tight complex. Right, a tight complex is a combinatorial analog of a tight embedding of a manifold into a Euclidean space. Right, now let M be a closed connected manifold. Okay, in the sequel, a manifold will mean a closed manifold, okay? And let M be a closed connected manifold. And the very classical result of Chern and Lashoff shows that the total absolute curvature of an embedding of M into the Euclidean space is bounded below by the number of critical points of some Morse function on M. Okay. The important point here is that the tight, all right, is this quantity is bounded below by the critical point of Morse function. Okay, so that, and of course the critical number of critical points of the number of critical points of Morse function is bounded below by the Betti numbers. So we have this corollary: the total absolute curvature of an embedding of M into the Euclidean space is bounded below by the sum of Betti numbers. All right, so with these results, we can define a tight embedding of a manifold. Okay, we said that an embedding of M into a Euclidean space is F-tight if its total absolute curvature equals to the sum of the Betti numbers of M over F. Right. So this is an edge condition like Golod. And these conditions are somewhat complicated because at least to me, because I'm not a specialist of differential geometry. But the next theorem gives me some intuition about tight embedding. Embedding F of M into Rn is F-tight if and only if the map from F of M, here's missing H, here's H. The intersection of F of M and H into Fm in homology is injective for almost half space H. This just means that that the M embedded in the Euclidean space, almost all height functions are Morse functions. So this just says that almost all such Morse functions are minimal. So every level set has no useless critical points. So if you embed two spheres like this, it's not tight. Right. All right. Now here's the let's define the tight complex. Okay, so the full subcomplex of K over the subset I of the vertex set of M is defined like this. It's the maximal subcomplex of K having the vertex set I. So the connected simplicial complex K is called F-tight if the inclusion of a Ki into K is injective in homology with coefficient in F for all non-empty subset I of bracket M. So this Ki is considered as the level set of the Morse function, like this. Right. So here's an easy observation. If K is F-tight, then it must be one neighborly. Okay. So then a triangulation of a circle is F-tight if and only if it is a triangle graph, which is the result we saw before. Right. Right. And let's see the, all right. So the tight embedding is somewhat economical embedding of a manifold into a Euclidean space. I mean, it doesn't bend unless it doesn't allow unnecessary bend of a manifold. So it may be one can so we can guess that the tight complex may be related to a minimal triangulation. Okay, so let's say that a triangulation K over space X is strongly minimal if for any K it has less or equal K simplices than any other triangulation of K. So it's really minimal. And here is a conjecture posed in 25 years ago. Every F-tight manifold triangulation is strongly minimal. Okay. Of course, it's almost impossible to check the strong minimality of a triangulation, but this is a nice, if this conjecture is true, then we get a nice criterion for the strong minimality of a triangulation of a manifold. And actually, the conjecture was verified in dimension 2 by the guys who posed this conjecture, and in dimension 3 in 2017. Right? It's really hard to check this conjecture. Okay, so the Golodness may be related to minimal triangulation, and tightness is conjectured to imply the minimality of a triangulation or manifold. So we can ask this question: is there a relation between Golodness and tightness for manifold triangulations? This is a very optimistic question, but I think this is interesting. All right, so here's another concept, another property of manifold triangulations. A D-manifold triangulation K is called tight neighborly if this equality holds. M is the number of vertices of K, and D is the dimension of a manifold, and here's the Betti number of a manifold, first Betti number of a manifold. So this equality is much easier to check than tightness and Golodness, because we only have to compute the first Betti number. And actually, and it seems that the equality depends on the ground field F, but in fact, it's independent. So this is a very easy, this is an equality to check easily. Okay, and here's a proposition. Tight neighborly triangulations are vertex minimal. Vertex minimal means that the number of vertices are minimal among any triangulation. Right? And there is a result connecting the tightness and tight neighborliness. Okay, let K be a triangulation of a D manifold where D is at least 3. And we consider these two conditions, K is F-tight and K is tight neighborly. And they prove Baguchi, Data, and Sprayer prove that 1 implies 2. And if these 3, the converse is also true. Okay. Sorry, this is not. Sorry, this is not true. 2 implies 1. Sorry, 2 implies 1. Sorry. So tight neighborliness is stronger than tightness. Right. So the tight neighborliness is a criterion for the tightness. All right, and Irie and I proved that proved a relation among Golodness, tightness, and tight neighborliness, and a moment-angle complex. Okay, let K be a triangulation of an F-oriented D manifold where D is at least 3. And consider the following 4 conditions. K is F Golod, K is F tight, K is tight neighborly, and ZK is a suspension. Then we get these implications. 1 implies 2, so okay, Golodness implies tightness. And 3 implies 2. 3 implies 2 is the result of Baguchi and others. And 3 implies 4. This is a topological part. And 4 implies 1. This is already, we already saw this. And in dimension 3, we know that the converse of this implication holds. So all of these conditions are equivalent. Right? And Golodness, tightness, and tight neighborliness, and ZK being a suspension are all equivalent. So, right. So up to dimension 3, we saw that tightness and Golodness of a manifold triangulation are equivalent, right? So we can ask this: are Golodness and tightness equivalent for manifold triangulations? Right. Actually, a weak version of Golodness implies a tightness like this. Okay, let's say that K is weakly F Golod if products in the causal homology of Fk vanish. So we forget about conditions on massive products and higher massive products in Golodness. That's weak Golodness. And Yuri and I proved that if K is a triangulation of an F-oriented manifold and it is weakly F-Golod, then it is F-tight. Okay. We proved this implication by using Poincare duality. So we need a simplicial complex K to be a triangulation of a manifold. Right. So here's a remark. In dimension up to 3, all higher massive products in Kozu homology of the Stanley-Reisner ring are trivial. That's from the degree reason. But in dimension greater than 3, there may be non-trivial higher massive products. So the inverse implication may be very difficult because we have to check all massive products and all higher massive products. Right. Yeah?
Is there a class of simplicial complexes which imply that, for which cup products 0 imply Golodness? I know they're not equivalent.
No, I mean, okay. That's tight complex. That's tight complex, actually. Okay. Right, that's a very good question. I mean, because in general, weak Golodness doesn't imply Golodness, but there are some classes, but it's not very big so far. I found a big one. Right, here's the main result. Okay, if K is an F-tight complex, then it is an F-Golod complex. Right. So combining with this result, we get these corollaries. Let K be a triangulation of an F-oriented manifold. Then K is F-Golod if and only if it is F-tight. This is interesting in the sense that these are Golodness and tightness have very different origin and have been studied in very different contexts, but they are actually equivalent for manifold triangulations. And here's the answer to Tony's question. Let K be a triangulation of an F-oriented manifold, then K is F-Golod if and only if it is weakly F-Golod. This is surprising to me because the conditions on massive products and higher massive products are redundant in the case of a triangulation of a manifold. Right. And there are more corollaries, but let me skip them here. All right, here is a very, very, very brief sketch of the proof. Okay, the proof is based on the combinatorial treatment of a DGA, which is equivalent to the Kozu complex of FK. We define the DGA C star of K like this. C0 is F and CP is the sum of reduced simplicial cochain complex of Ki. And the product of C star K is given like this. This is induced from the inclusion of Ki cup J into Ki join Kj. All right. And this DGA is motivated by the cellular chain complex of ZK, which was given in the talk of Stephen before. And so, right, here's the important proposition. The DGA C star of K is homotopy equivalent to the Kozu complex of the Stanley-Reisner ring of K. So we can check the triviality of all massive products and higher massive products in the Kozu homology of Fk by considering the DGA C star of K. And the point is, the important point is here is that the C star of K is given purely combinatorial. Right. And okay, to check the triviality of all massive products and higher massive products and products in the cohomology of this DGA C star K, we have to consider higher homotopies in it, of course. Right. But as far as I know, there is no result about higher homotopies among simplicial complexes, so I have to construct it. Right. The main ingredient of the proof is the construction of the higher prism operator. Okay. Okay, let's choose a total order on the vertex of a simplicial complex. Okay. We always have a total order on the vertex set. Then we can define K tensor K of simplicial complexes K and L, okay, which triangulates the realization of K cross the realization of L. Okay, this is just a very standard construction, like prism decomposition. Right now, here's the higher prism operator. Okay, suppose we have a simplicial map H from K tensor delta to the Q into L. Then we get a map PH from C star L to C star minus Q of K, satisfying this coherent conditions. Okay. Here, where d to the I is the ith coface operator from delta Q minus 1 into delta Q. All right, I skipped the construction of pH because it's really complicated. We have, all we do is, okay, we have to classify all lattice paths and count the number of lattice paths in all classes and then construct this pH. That's really complicated. But the important point here is this coherent property. Okay, so for example, if Q is 0, then pH is H. If Q is 0, H is just a simplicial map from K to L. And in that case, pH is H. Okay, if Q is 1, then our prism operator, higher prism operator, pH is the usual prism operator. Okay, and let's see. Okay, delta pH plus pH delta, which is given by this equation, is exactly the same as P of H restricted to 1/10 of D0 and minus P of BH restricted to H to 1/10 of D1. And it is nothing but H restricted to K tensor 1 minus H restricted to K tensor 0. This is nothing but the prism operator for H. Okay. Now, we proved the main theorem by applying higher prism operators to the DGA C star of K. I mean, we proved the triviality of the massive products and higher massive products under the assumption that K is F-tight. And actually, the tightness of K is only used to lift a cocycle in Ki to K. So, I mean, the tightness is only used to the first step of the induction. The induction goes by using this pH. So tightness doesn't use to the further steps in the induction. All right, that's all. Thanks.